Hello students, today we are going to discuss the topic carbonyl compounds. What are called carbonyl compounds? The compounds which contain a carbonyl group are called carbonyl compounds. What is a carbonyl group? Bond CO bond group is called carbonyl group. Those organic compounds which contain CO as a function group are called carbonyl compounds. These carbonyl compounds are further classified into aldehydes and ketones. Today we are going to discuss in detail about the carbonyl compounds. In this topic we are going to discuss the nomenclature of carbonyl compounds, preparation of carbonyl compounds, and physical properties of carbonyl compounds. Now let us discuss the definition of aldehydes and ketones. The carbonyl compounds which contain bond CO bond group are called aldehydes and ketones. Those carbonyl compounds in which bond CHO is present as a function group are called aldehydes, and those carbonyl compounds in which bond CO bond C bond CO bond C is present as a function group are called ketones. So both aldehydes and ketones are collectively known as carbonyl compounds. General formula of aldehydes is R bond CHO, where R may be H, alkyl or aryl group. If R is equal to H, we can write H bond C double bond O bond H. This is formaldehyde. We also call it as methanol. We will discuss why it is also called methanol. Next, second example for aldehydes is CH3 bond CHO. This is acetaldehyde. This acetaldehyde is also called ethanol. Third example for aldehydes is benzaldehyde, C6H5CHO. General formula of ketones. Already I told you, the carbonyl compounds which contain C bond CO bond C as a function group are called ketones. The general formula of ketones is RCOR1, where R1 may be or aryl group. So fundamental difference between aldehydes and ketones is that in aldehydes at least one H atom is present, whereas in ketones no H atom is bonded with CO group. That is a fundamental difference between aldehyde and ketone. In any aldehyde at least one H atom is bonded with CO group, whereas in ketone CO group is not bonded with any hydrogen atom. It means that in aldehyde one of the two valencies of CO group is bonded with hydrogen, whereas in ketones both the valencies of CO group are bonded with alkyl or aryl group. Examples for ketones: acetone CH3 bond CO bond CH3, that is also called propanol. Second example for ketones is butanol butanone. We also call it as ethyl methyl ketone. Third example for ketones is phenylethanol. Phenylethanol C6H5 bond CO bond CH3. Let us discuss the type of bonding in CO group. In a CO group, the C atom is sp2 hybridized. As we know that if any molecule, if a central atom is sp2 hybridized, then the structure of that molecule must be triangular planar and bond angle in that molecule must be 120 degrees. The sigma bond in a CO group, 1 sigma and 1 pi bond is formed. The sigma bond is formed by the head-on overlap of an sp2 hybrid orbital of carbon and 1 p orbital of oxygen. The pi bond is formed by the sidewise overlap of p orbitals of carbon and oxygen. You can also see the formation of sigma and pi bond between the orbitals of carbon and oxygen. In between carbon and oxygen, initially sigma bond will be formed. After the formation of sigma bond, pi bond will be formed. So sigma bond is formed by the head-on overlapping between sp2 hybrid orbital of carbon and p orbital of oxygen. Whereas a pi bond is formed between a p orbital of carbon atom and a p orbital of oxygen atom. The three atoms that are bonded to the carbonyl carbon forms a trigonal planar structure. The three atoms that are bonded to the carbonyl carbon forms a trigonal planar structure. The bond angles between three attached atoms are 120 degrees, nearly 120 degrees. You can see the structure of aldehyde or ketone. RCOR is ketone, RCHO is aldehyde. Whether it is aldehyde or ketone, in any carbonyl compound, the bond angle must be 120 degrees and the structure of a carbonyl compound, maybe aldehyde or ketone, must be triangular planar structure or trigonal planar structure. Since oxygen is more electronegative than carbon, so naturally carbon atom gets partial positive charge, oxygen atom gets partial negative charge. Because of the high electronegativity of oxygen, bonded electron pair will be slightly shifted towards oxygen atom. Due to the high electronegativity of oxygen, the bonded electron pair between carbon and oxygen will be slightly shifted towards oxygen atom. Due to this, carbonyl oxygen gets partial negative charge, carbonyl carbon gets partial positive charge. So, CO group present in aldehyde or ketone is a polar group. Now we shall discuss about the nomenclature of carbonyl compounds. Aldehydes are also called alkanols. Why? Aldehydes are named by replacing the final E of the alkane of the corresponding alkane with al. So, in IUPAC system, of nomenclature. Aldehydes are also called alkanols. Examples: H bond CHO. This is formaldehyde. Formaldehyde is the simplest example of aldehydes. In IUPAC system, this formaldehyde is called methanol. Methanol is the IUPAC name of formaldehyde. Since one carbon atom is present, the root word is meth, single bonds are there, and the parent hydrocarbon of methanol is methane. So the suffix E is replaced by al. Therefore, methanol will be the IUPAC name of formaldehyde. Second example for aldehydes is CH3 bond CHO. This is acetaldehyde. The IUPAC name of acetaldehyde is ethanol. Why? Because two carbon atoms are present. Parent hydrocarbon is ethane. In ethane, the last letter E is replaced by al. Therefore, the IUPAC name of acetaldehyde is ethanol. Two more examples are also seen. 3-hydroxypropanol. 3-hydroxypropanol. Propanol is propanoldehyde, is also called propanol. Counting must be done from right to left because function group is present in a chain. Whenever function group is present in a chain, the carbon to which function group is attached itself is considered as the first carbon. Since third carbon has OH group, we call it as 3-hydroxypropanol. Phenylethanol. Phenylethanol. Since the hydrogen atom of CH3 is replaced by phenyl group, we call it as phenylethanol. Propanol. Propanoldehyde is also called propanol. Benzaldehyde, there is no IUPAC name of benzaldehyde. Common name is benzaldehyde and there is no specific IUPAC name for benzaldehyde. Now let us see the nomenclature of ketones. Ketones are named by replacing the final E of the name of the corresponding alkane with -one. The parent chain is then numbered in the way that gives the carbonyl carbon atom the lowest possible number, and this number is used to indicate the position. See, in IUPAC system of nomenclature, ketones are also called alkanones. Alkanones. The E of alkane is replaced by ONE. Therefore, all ketones are also called alkanones. Examples: propanone. Propanone. Parent hydrocarbon of propanone is propane. So propanone is the IUPAC name of acetone. Butanone is the IUPAC name of ethyl methyl ketone. Pentanone. Pentanone. This is methyl propyl ketone. Methyl propyl ketone. Pentanone. Pentan-3-one. Here carbon group is found on third carbon atom, therefore pentan-3-one. Cyclohexanone, phenylethanone are the various examples for ketones. Some more examples of aldehydes and ketones are found. Butanol. Butylaldehyde is also called butanol. Butanone. Butanone is an example for ketones. Methyl propanol is an example for aldehydes. Similarly, pentanol. is an example for aldehydes. Pentan 2-ol, pentan 3-ol are the two different examples of ketones. Look at the physical properties of carbonyl compounds. Simple aldehydes and ketones are gases or liquids at room temperature. Simple aldehydes and ketones are gases or liquids at room temperature. Aliphatic aldehydes have unpleasant and pungent smell. Ketones and benzaldehyde have a pleasant and sweet smell. Next, you can see the boiling point, melting point and densities of different aldehydes. Look at the boiling points, melting points and density values of different aldehydes. Methanol, ethanol, propanol, butanol, etc. From methanol to butanol and so on other groups, as the molecular weight of an aldehyde increases, boiling point values are also increasing. Boiling point values are also increasing and melting point values are also increasing. But some irregularities are also found in the melting points. Densities are increasing, but some irregularity is found in densities also. So boiling points are continuously increasing as the molecular weight of an aldehyde increases. If you look at the boiling point and melting points of and densities of ketones, as the molecular weight of a ketone increases, boiling points are also increasing continuously. So when we compare the boiling points or melting points of aldehydes and ketones, ketones have higher boiling points and melting points than corresponding aldehydes. When you compare the boiling point and melting points of carbonyl compounds with those of hydrocarbons, carbonyl compounds have higher boiling point and melting point than hydrocarbons of similar relative molecular masses. So this is an important thing. Carbonyl compounds, both aldehydes and ketones, have higher melting and boiling points than corresponding hydrocarbons. Why carbonyl compounds have higher boiling point and melting point than corresponding hydrocarbons? It is because of the presence of dipole-dipole interactions. See, in carbonyl compounds we can find dipole-dipole interactions, whereas dipole-dipole interactions are not found in hydrocarbons. Due to the presence of dipole-dipole interactions, carbonyl compounds have higher boiling point and melting point. One more thing, carbonyl compounds have lower boiling point and melting point than the corresponding alcohols. When we compare the boiling point and melting point of carbonyl compounds with those of hydrocarbons, these carbonyl compounds have higher boiling point and melting point than corresponding hydrocarbons. When we compare the boiling point and melting point of carbonyl compounds with those of alcohols, carbonyl compounds have lower boiling point and melting point than the corresponding alcohols. The question arises, why carbonyl compounds have lower boiling point and melting point than the corresponding alcohols? Due to the presence of dipole-dipole interactions. Dipole-dipole interactions are present in all carbonyl compounds, but these interactions are weaker than intermolecular hydrogen bonds. Remember, alcohols contain intermolecular hydrogen bonds. whereas carbonyl compounds contain only dipole-dipole interactions. These dipole-dipole interactions are weaker than intermolecular hydrogen bonds. Therefore, carbonyl compounds have lower boiling point and melting point than the corresponding alcohols. That can be easily understood when we see the graphs. In this graph, aldehydes and ketones are seen in the middle and alcohols are seen in the upper part, and alkanes are seen in the lower part. So we can conclude that the boiling point and melting point of aldehydes and ketones are higher than corresponding alkanes but lower than corresponding alcohols. Solubility. Aldehydes and ketones of low molecular masses show appreciable solubilities in water. Carbon and oxygen can form strong hydrogen bonds with water molecules. We can see the hydrogen bonds exist between carbonyl compound and water. Listen, here carbonyl group is a polar group. Water is also a polar molecule. So there is a possibility of intermolecular hydrogen bonds. So aldehydes and ketones are highly soluble in water, easily soluble in water, because molecules of carbonyl compounds can form hydrogen bonds with water molecules due to the possibility of formation of intermolecular hydrogen bonds. Aldehydes and ketones are easily soluble in water. Example, propanone and ethanol. Propanone and ethanol means acetone and acetaldehyde are soluble in water in all proportions. Means we can dissolve less quantity of alcohol, less quantity of ketone in more quantity of water, or more quantity of ketone can be dissolved in less quantity of water. Anyhow, propanone and ethanol are soluble in water in all proportions. Preparation of carbonyl compounds. Now we are going to discuss the preparation of methods of preparation of carbonyl compounds, particularly both aldehydes and ketones. Preparative methods can be compared comparatively. The methods of preparation can be studied comparatively. Since aldehydes and ketones are carbonyl compounds, their methods of preparation will have similarity. Industrially, lower members of aldehydes and ketones are prepared by passing alcohol vapor over hot silver catalyst. When we pass a primary alcohol, vapors of primary alcohol over silver catalyst at 300 degrees centigrade, we get an aldehyde. When we pass the vapors of secondary alcohol over silver catalyst at about 300 degrees centigrade, we get ketone. In these two reactions, dehydrogenation takes place. Removal of hydrogen is called dehydrogenation. Here, silver, powdered silver is used as a catalyst. So, a primary alcohol on dehydrogenation gives an aldehyde, whereas a secondary alcohol on dehydrogenation gives a ketone. So, dehydrogenation of alcohols is one of the methods to prepare aldehydes and ketones. Second method is oxidation of alcohols. Oxidation of alcohols. By the process of oxidation of alcohols, we can also prepare aldehydes and ketones. Only the thing is that to prepare an aldehyde, primary alcohol must be taken. To oxidize, by the oxidation process, primary alcohol must be taken for aldehydes, secondary alcohol must be taken for ketones. Example of oxidizing agents: acidified potassium dichromate. Aldehydes are prepared by oxidation of primary alcohols. If OH group is bonded with a primary carbon, such alcohol is called a primary alcohol. Primary alcohols, upon oxidation with acidified K2Cr2O7, gives an aldehyde. That can be seen in the equation. RCH2OH gives rise to RCHO. Secondary alcohols upon oxidation give a ketone. So ketones are prepared by oxidation of secondary alcohol. RrCHOH gives rise to K2Cr2O7 oblique H plus reflux RCOR1. It means that a secondary alcohol on oxidation by acidified potassium dichromate gives a ketone. Anyhow, by the oxidation of primary alcohol we get an aldehyde. By the oxidation of secondary alcohol we get a ketone. Oxidative cleavage of alkenes. Third method to prepare carbonyl compounds. Oxidative cleavage of alkenes. Ozonolysis. So by means of ozonolysis we can also prepare aldehydes. Ozone reacts with alkenes vigorously to form ozonides. Ozone reacts with alkenes to form ozonides. Ozonides are reduced by zinc and water to give aldehydes and or ketones. Ozonolysis is one of the methods to prepare aldehydes or ketones. In this process, an alkene reacts with an ozone giving rise to ozonide, alkene ozonide. This ozonide is a cyclic, intermediate, unstable and explosive compound. Since ozonide is an unstable cyclic compound, it undergoes cleavage in the presence of zinc, dust and water, giving rise to aldehydes and or ketones. Third method to prepare aldehydes and ketones is decarboxylation of acid salts. Decarboxylation of acid salts. Aldehydes, decarboxylation means removal of CO2. Aldehydes can be prepared by heating a mixture of calcium methanoate and calcium carboxylate. In general, acetaldehyde is prepared by heating a mixture of calcium acetate and calcium formate. When a mixture of calcium acetate and calcium formate is heated to very high temperature, upon dry distillation we get acetaldehyde. So by the decarboxylation of acid salts we can also prepare aldehydes and also ketones. Ketones can be prepared by heating calcium carboxylate. Example, calcium acetate on strongly heating gives acetone. So both aldehydes and ketones can be obtained by the decarboxylation process. Acetaldehyde can be obtained by heating a mixture of calcium acetate and calcium formate, whereas acetone can be obtained by heating a mixture of calcium acetate only. One more method to get aldehydes and ketones: reduction of acyl chlorides. Reduction of acyl chlorides. Aldehydes can be prepared by reducing acyl chlorides by treatment with hydrogen in the presence of palladium and barium sulfate catalyst and sulfur. The purpose of adding sulfur is to poison the catalyst. so that reduction does not proceed to produce alcohols. So acyl chlorides. From acyl chlorides we can also prepare aldehydes. RCOCl is acyl chloride. This acyl chloride, upon reduction in the presence of palladium and barium sulfate, palladium and barium sulfate in the presence of sulfur gives aldehyde. So in this process, RCOCl becomes RCHO, means chlorine is replaced by H. Removal of chlorine, addition of hydrogen. Removal of chlorine is reduction, addition of hydrogen is also reduction. So acyl chloride is reduced to aldehyde. So by these methods we can prepare aldehydes and ketones. Since aldehydes and ketones are collectively known as carbonyl compounds, they show similarity in their preparation and properties. Preparative methods are similar and properties of aldehydes and ketones are also similar. Just they vary in few properties only. So in the next class we will discuss the reactions of aldehydes and ketones. In those reactions of aldehydes and ketones, we will discuss nucleophilic addition reactions. Aldehydes undergo nucleophilic addition reactions, ketones also undergo nucleophilic addition reactions because both aldehydes and ketones contain same group, CO group. Since CO group is a polar group, carbon of carbonyl group gets partial positive charge and oxygen of carbonyl group gets partial negative charge. Why carbon gets partial positive and why oxygen gets partial negative? Because of the high electronegativity of oxygen, the bonded electron pair between carbon and oxygen will be slightly shifted towards oxygen, so that carbon gets partial positive charge and oxygen gets partial negative charge. Because of the polarity existing in a carbonyl group, nucleophilic attack will occur. Aldehydes and ketones both undergo nucleophilic addition reactions. Similarity is there between the reactions. Addition of sodium bisulfite. Example, addition of sodium bisulfite. This reaction occurs both in aldehydes and ketones. Second one, addition of ammonia. This reaction also occurs both in aldehydes and ketones. Addition of hydrogen cyanide. This reaction also occurs both in aldehydes and ketones. Most of the chemical reactions of aldehydes and ketones are similar. So, since aldehydes and ketones possess similar chemical properties, they differ only in their function group. So there are separate tests to identify aldehydes and ketones. Tolerance test. Ammonical silver nitrate solution is called tolerance reagent. Ammonical silver nitrate solution is called tolerance reagent. So in tolerance test, by tolerance test we can identify aldehydes from ketones, because only aldehydes can give tolerance test, whereas ketones do not give. Similarly, Fehling test. Alkaline solution of copper tartarate. Alkaline solution of copper tartarate is called Fehling solution. So, by Fehling test we can identify aldehydes from ketones, because only aldehydes give Fehling test, ketones do not give Fehling test. So in Fehling test, the alkaline solution of copper tartarate, when we add Fehling solution to aldehyde, immediately copper will be precipitated. Red copper will be precipitated. Cuprous oxide will be obtained as a red precipitate. So ketones cannot give failing test. Only aldehydes give failing test, ketones do not give failing test. Similarly, only aldehydes can give tolerance test, whereas ketones do not give. In tolerance test, aldehydes form silver mirror, whereas ketones do not form silver mirror. So, both aldehydes and ketones can be distinguished by two tests. Number one, tolerance test. Number two, failing test. So, in the next video lesson, we will discuss in detail about the reactions of aldehydes and ketones. Thank you. Stop. Video stop.